us about
very long title. So also known as a polynomial time algorithm for non-commutative rank. The reason I prefer this is because this is the way I came to this problem. So this is joint work with Gabor and Yoming. So let me just, so what I will do is I'll spend a lot of time on the background, actually not really give you much details. So the background, so this is the outline. So let us get to the background. So so you have a collection of matrices x1, x2, xm. Each xi is an n cross n matrix with entries xij superscripted by k. And there is a natural action of SLN cross SLN, that is you are looking at matrices of determinant 1. They take a tuple of matrices. So you give me a tuple, m tuple of matrices and give me a pair in a pair of matrices. Then naturally x1, x2, xm go to ax1 b transpose, ax2 b transpose, axm b transpose. So this is how SLN cross SLN is acting on tuples of matrices. And there are some classical invariant theory questions. One is what are polynomial functions that are invariant under this action? That is, if I evaluate that function, it should remain the same along the entire orbit. So this is really well understood in characteristic 0. So there are a lot of results rediscovered many times, even over infinite fields. Then the classical results also tell you that the ring of invariants, so the invariants actually form a ring. If A is an invariant, B is an, if F is an invariant, G is an invariant, F plus G is an invariant, F times G is an invariant, and so on. So you have a ring, and this ring is known to be finitely generated, and a natural question is the bound in which the generators lie, the bound on the degree in which the generators lie. So from classical work of Dirksen, it follows that you can actually show that generators can be chosen to have degree exponential in n squared. Note that this is independent of the m that you have. So what are the actual invariants? Well, it's quite easy to sort of produce invariants. For example, if I just look at this block matrix, so this will be a 3n by 3n matrix, and I take its determinant, then this is going to be an invariant, because what happens is each of the xi's just gets pre and post multiplied by ax, a and b transpose, and you can pull out the a on this side, pull out the b on the other side, and since a and b are assumed to be of determinant 1, this determinant remains the same. So furthermore, determinants of this type also remain invariant. In fact, the coefficients of Tij k here that I have written down, each individual coefficient is actually invariant. And in fact, this is a total description of the invariants. So it turns out that you can take matrices T1, T2, Tm in your base field and look at the determinant of T1 Kronecker product x1 plus T2 Kronecker product x2 and so on. This is actually an invariant. This is an invariant of degree n times d. And over infinite fields, one can actually show that these are all the invariants. All invariant functions are really specializations of determinants. So now, what is the null cone, which is part of the title? So if I give you an invariant ring and I give you a tuple of matrices, the same size, and I say b1, b2, bm is in the null cone if every invariant polynomial function vanishes on this tuple. So it turns, so there is an alternate characterization of, so this is the definition, and one would like a good characterization. So it turns out that, so this is the connection with non-commutative rank. So it turns out that b1, b2, bm is in the null cone if the matrix space B, script B, matrix space script B being look at the linear combination of b1, b2, bm with coefficients coming from my base field f. So that is the matrix space that we are talking about. If the matrix space has a C shrunk subspace for some constant C, for some number C bigger than 0, for an integer C bigger than 0. Now what is a shrunk subspace? Well, this is the final definition that you will need. So I have a collection of matrices. I'm looking at the F linear span of these matrices. So we say a subspace U is shrunk by script B if the dimension of script BU, which is look at B1, apply it on U. So you look at the image of U under B1, look at the image of U under B2, look at the image of U under BM, and take the linear span of that. If the dimension of that is smaller than the dimension of U by a factor, by the number C, then I say it is C shrunk. And so it turns out that B1, B2, Bm is in the null cone if and only if there is a subspace that all of them shrink. And as Nikhil pointed out, this is the connection with bipartite matching in some sense. The non-commutative rank, so this is an equivalent definition. The non-commutative rank is defined, was defined earlier, actually quite sometime in the early 70s. And then Fortin and Rotenier showed that there is an alternate way of defining non-commutative rank. So the non-commutative rank makes sense for a matrix family. So for a matrix family B, the non-commutative rank is the n minus the dimension, the largest subspace that is shrunk by B. Now, and the natural question here is, what is the non-commutative rank of a matrix family that is presented to you? So what you're given is a basis of B. So of course, the related problem is the celebrated PIT problem that we are looking at. If I give you a family of matrices and I want to know the matrix of largest rank in B, and that is, in general, we don't know how to do this, and that is something we would really like to know. This goes back to Edmonds in '67, and it's clear that the rank is less than non-commutative rank, because if the entire family shrinks a subspace, then of course the rank of of every matrix in that is less than the codimension of that subspace. And it is also true that this is a strict inequality. For example, if I look at 3 cross 3 skew matrices, then because they are skew matrices, all of them have eigenvalue 0. They all shrink a subspace, but they don't shrink a common subspace. So in fact, inside the family of 3 cross 3 skew symmetric matrices, there is actually the non-commutative rank is actually 3, because they don't shrink a subspace, but no matrix has rank more than 2. In fact, 2 is the largest rank. So when it comes to this problem, the earliest known result on this was a theorem of Gurwitz, which worked under a promise actually. So it worked under the promise that if your inputs are guaranteed to be of the following kind, if your matrix space is guaranteed to have commutative rank n, or non-commutative rank strictly less than n, then Gurwitz actually had a deterministic polynomial time algorithm for this, and this was the motivation for Gabor and Yoming when they came to this problem. Wanted to see if they could extend Gurwitz's results. So of course, by what we just observed, this algorithm could give a wrong answer in instances which don't satisfy the given promise. Yeah. So let us just see some simple properties of a matrix space. So if B1 shrinks a subspace, and if I take any matrix, any D cross D matrix, then if I look at the Kronecker product of B1 tensor T1, that of course shrinks the subspace U tensor F to the D. In fact, if script B shrinks a subspace, then all its D blow-ups, what is the D blow-up? The D blow-up of B is naturally defined. You look at what happened? Oh, sorry. Yeah, so the D blow up of the matrix space B is the linear span of B1 tensor T1, B2 tensor T2, Bm tensor Tm, where Ti's are arbitrary matrices over the base field. Then by the previous simple observation, if B shrinks a subspace, then of course the D blow up also shrinks a subspace. Yeah? Yeah, 1 minute, yeah. So it will be done. So if B does not shrink a subspace, then by definition, by our alternate characterization, B is not in the null cone, which means because all our invariants are of that kind, invariants are of the kind T1 tensor B1, T2 tensor B2, Tm tensor Bm. So then we know that BDD better have a non-singular matrix, because there is an invariant polynomial actually which does not vanish then. But then this means that there is an invariant polynomial that witnesses non-membership in the null cone. And that is what we are actually looking for. So let me just give a brief description of what our main results are. So these are informal statements. So the first statement is that when I take a D blow up, then, and if I look at the commutative rank, the matrix with largest rank inside the Dth blow up, then it turns out that that rank is actually divisible by D. Then the other thing that we have is a constructive version of this regularity lemma. That is, if I give you, so if I give you a matrix in the Dth blow up which has rank R minus 1 times D plus 1, then you should be able to scale up the rank to be a multiple of D. So you can in fact get a matrix of rank R times D in that. We also show that this can actually be done constructively. There is the third statement on which our results are based is what we call constructive progress, which says that if you give a matrix of rank R times D in the Dth blow up, then by further blow up, by looking at D prime blow up of your underlying matrix space, you can either show that you shrink a subspace in the D prime blow up, or you can actually augment the rank by at least 1. And it is this augmentation which is done by a sort of augmenting path kind of algorithm, which was known by previous work of Gabor, Jimmy, Mikolos Santa actually. I will just zip through that. So this actually immediately implies, our previous three observations immediately imply an exponential time algorithm. So I'll just take one more minute and then describe what was known, soon after we published this result on the exponential time algorithm. GGOW, Garg, Gurwitz, Oliveira and Vigdersen showed a polynomial time algorithm for membership in the null cone. Then this was improved by Dirksen and Markham, who showed that there is an n squared degree bound on the generators of the ring of invariants, which is a remarkable result actually. Then what we did was we observed that we can actually constructivize their results actually, and in fact there is a far simpler proof of the results in Dirksen and Markham. So maybe I'll just stop at this point. The proof ingredients are that actually you don't have to blow up too much. Blow up of up to n plus 1 suffices. That is the crucial point actually, and that is some argument that we missed. It's a rather straightforward argument actually. And the other thing is, for constructivizing it, we need to construct a division algebra D inside our matrix space, an extension of MDF actually. And one can show that if I tensor it with matrices inside the division algebra, then in fact the regularity lemma actually follows, that all matrices here have rank divisible by D. This follows from and the last thing, the use of second Wong sequences. So I'll just halt with this. And this is the motivation for me is still to try and understand the determinate orbit closure using this. Yeah. So if there are any questions.